Now we come to the second part of the wave-particle duality. When light hits an electron, light acts like a particle. And a particle is always discrete. So that means you have one particle, you have another particle, and a third particle. And one particle can only be at one point in space at the same time. And as you saw before, a wave can be at many locations at the same time. Photon is the name for a light particle, and the abbreviation for photons is gamma. Gamma is Greek for the small g. A photon has no mass. That is why it can travel at the maximum speed possible. That is the speed of light, c. Nothing can travel faster than the speed of light, c. A photon contains energy. That is photon energy. What is energy? That is not easy to answer, but we can give you an example. For instance, if lifting an object from the ground requires energy. The unit for energy is the joule, Joule, abbreviated as J. And J is equal to kilogram multiplied by meter squared divided by second squared. Let me tell you exactly when you have spent 1 joule of energy. Push an object with a mass of 1 kilogram for 1 meter while accelerating it from 0 to 1 meter per second squared. Then you have used energy of 1 joule. The most famous energy formula is Einstein's E equals mc square joules. J, kilogram multiplied by meter square divided by second square. And the m is mass, and this c is the speed of light. And please don't be confused that you find m in the energy formula, but it is also part of the unit. Once this is mass, but here it is meter. That is a little bit confusing, but when you see where you find the m, you will know which one is mass and which is meter. So kilogram is the unit for mass, and m meter is the unit for distance or length. The third observation is that one photon of light with the same wavelength, for instance 656 nanometer, moves one electron always into the same orbit. Fire photons of 656 nanometer wavelengths and the electron is pushed into the red orbit. Do it again here. Red photon, red orbit. It is always into the same orbit if you use the same wavelengths of photon. Always into the red orbit. Never in a red photon into the green orbit, into the larger orbit. This means the electron is moved from the ground state into an excited state by absorbing the energy from a photon. Think of it this way. It requires energy to push an electron into a larger orbit. And photons are carrier of energy. Think of it like a billiard ball hitting a second ball. Now the second ball has more energy than before. Now you need to make an important conclusion. as each photon with a given wavelength moves the electron always into the same orbit, all photons of a given wavelength must contain the same amount of energy. So each photon with a wavelength of 656 nanometer must contain an amount x of energy, and each photon with a wavelength lambda 656 nanometer contains exactly the same amount of energy. The person who discovered this first earned a Nobel Prize. Each photon of light with the same wavelength contains the same amount of energy. A photon contains an energy quantum. That is what that means. A quantum is the minimum amount of any physical entity involved in an interaction. And quantum, plural quanta, how much? This means the energy of a photon is quantized. The person who discovered in 1900 that each photon of a given wavelength contains a specific energy package is Max Planck. For this, he received a Nobel Prize in 1918. The Planck relation calculates the energy quantum of a photon given the photon's wavelength, lambda. So the Planck relation is E of the photon equals h multiplied by c divided by lambda. And this is all in joule. The only thing that is new for you in this equation is the Planck constant h, which has the value 6.626 multiplied by 10 to the power of minus 34 joule second. This is one of the most important constants in physics. It is similar to the speed of light, c, which is 3 multiplied by 10 to the power of 8 meter per second. And there's nothing really to think about. The only thing is you could memorize this Planck constant to have it always available in your mind. It is not that difficult. This is h equal 6.626 multiplied by 10 to the power of minus 34. So even I can memorize it. I close my eyes and I say h equals 6.626 multiplied by 10 to the power of minus 34. And if you want to be very precise, you say the dimension is joule multiplied by second, joule second. Now you are able to calculate the energy of a photon with the wavelength 656 nanometer. And it is very simple. You just have to multiply h and c, the Planck constant, with the speed of light, which you see here, that is about 19.8 multiplied by 10 to the power of minus 26. And then you divide that by lambda, which is 656 multiplied by 10 to the power of minus 9. And you get an energy quantum for a photon of light with a wavelength 656 nanometer of 3.0 multiplied by 10 to the power of minus 19 joule. Please check this calculation and make sure that I did not make any mistakes. Another observation we make is that one photon always reacts only with one electron. It is never 1/2 photon and 1 electron, because photons and electrons are quantized. You cannot cut an electron in 1/2 and still have an electron. And you cannot cut a photon in 1/2 and still have a photon. They are not divisible. If you would divide them, you would get something totally different. It is also true that 2 photons never combine with 1 electron. So you can never take the energy of 2 red photons and put it into 1 electron, because electrons do not accumulate photons. It is always 1 red photon and 1 electron. It is never 2 red photons and 1 electron. This was discovered by Einstein in the photoelectric effect in 1905, and he won his Nobel Prize explicitly for this discovery. So let's make that clear. If we take a photon with a wavelength of 656, you see 1 photon and 1 electron. It cannot accumulate photons. It cannot combine 2 photons with 1 electron. This is Einstein's discovery and was very important discovery in physics. Always 1 photon and 1 electron. When we analyzed our Bohr models, we found that the larger the wavelength lambda of the light, the smaller the new orbit. So let's start with the lowest, with the shortest wavelength, which is 410 nanometer, and you see it goes into the largest orbit. Now let's look at the 656, which is a much larger wavelength, and it goes into a smaller orbit. Of course, it takes more energy to push an electron into the higher orbit. Therefore, if lambda increases, the energy of a photon decreases. This follows directly from the Planck relation, E equals h multiplied by c divided by lambda, because the wavelength lambda is in the denominator. Here are the exact values for the energy of each photon with a given wavelength. So if the light has a wavelength of 656 nanometers, the energy quantum is 3.0 multiplied by 10 to the power of minus 19 joule. If the wavelength of the light is 486 nanometer, the energy quantum is 4.1 multiplied by 10 minus 10 to the power of minus 19 joule for each photon of that light. If the wavelength is 434 nanometers length, then the energy quantum of the photon is 4.6 multiplied by 10 to the power of minus 19 joule. And if the wavelength is 410 nanometers, each photon has an energy quantum of 4.8 multiplied by 10 to the power of minus 19 joule. The larger the wavelength of the light, the lower the energy quantum of the photon of that light. Our fifth observation was an excited electron emits a photon of light with the same wavelength that it had previously absorbed and falls back to its ground state. Well, that is pretty obvious that the photon represents energy, and an electron emits the same amount of energy it previously absorbed as a photon. Therefore, the electron needs to fall back to its ground state because it has less energy now. Our sixth observation was that only light with specific wavelengths is absorbed by the hydrogen atom. For the visible light, these specific wavelengths are lambda equals 410, 434, 486, 656 nanometers. When light with non-specific wavelengths hits the hydrogen atom, nothing happens. For instance, if you shoot photons of the wavelengths lambda equals 600 nanometer, then the electron will not react. Why is that? Let's try this simple explanation. There are only a limited number of orbits in an atom labeled n equals 1, 2, and 3, and so on. For the electron to be lifted into orbit 2, an energy quantum of x is required. Let's say x is equal to 3.0 multiplied by 10 to the power of minus 19 joule. This is the energy of a photon with lambda equals 656 nanometer. For the electron to be lifted into orbit 3, a larger specific energy quantum alpha is required. Let's say alpha is 4.1 multiplied by 10 to the power of minus 19 joule, which is the energy of a photon with lambda equals 486 nanometer. But there is no orbit 1.5. Therefore, an energy quantum greater than x equals 3.0 multiplied by 10 to the power of minus 19 joule, but smaller than y equals 4.1 multiplied by 10 to the power of minus 19 joule. Let's say, for example, 3.8 multiplied by 10 to the power of minus 9 joule will not lift the electron into a higher orbit. This is because there is no orbit 1.5. You need exactly the right amount of energy to lift the electron into a higher orbit.